Okay, Year 11s, and welcome to video number 2 in my ongoing Bringing Chemistry to Life series. Guys, today we're going to consider in a little bit more detail the theory behind how catalysts increase reaction rate. And remember that we've been doing some practical lab work that sort of demonstrates the role that catalysts play in increasing the rates of reactions. So we're sort of going to marry those two things. Today, the video, we've got our theory, and hopefully we can tie that in with the lab work that we've been doing. So guys, just before we launch into catalysts, I'd just like to quickly recap what the things that are required by reactant molecules to actually react and form products in the first place. So guys, if we pencil in here in the nice bold canary yellow colour, in order to form products here from our reactants, two things have to happen. Our reactant molecules have to overcome a certain amount of activation energy, and they also have to have some favourable collisions. That's better. Favourable collisions. So, guys, both of these things have to happen in order to form products. We have to have reactant molecules with energy higher than the activation energy, and they also have to favorably collide, and then and only then can we form new bonds in our products. Now, guys, I'd like to concentrate on this graph down the bottom for a minute because it considers the very important point of activation energy in any reaction. So, guys, this diagram shows us that for a particular reaction, the activation energy is this line here in purple. What that's telling you, Year 11s, is that at this particular activation energy, only this number of reactants here have got that amount of energy higher than the activation energy available to them to collide, react, and form products. Guys, that brings me, we'll go back to this in a minute. That brings me to this graph on the right hand side, which shows two reaction pathways for the same reaction. In red, we've got the uncatalyzed reaction pathway, and in blue, we've got the catalyzed reaction pathway. And hopefully you guys can very visibly see that the uncatalyzed reaction pathway has got a reasonably high activation energy. It's up here. I'll just pencil that in red. So what that means, Year 11s, is that these reactant molecules on the left-hand side have to possess this amount of energy in order to react and form products. Now, guys, it's fair to say that this activation energy is very, very high, and it's going to be unlikely that many reactant molecules have got this required energy. Because not many of these reactant molecules have this energy, then this reaction is unlikely to go ahead because we haven't fulfilled this aspect here. So, guys, what we can do in order to get a reaction to occur is to add a catalyst and decrease that activation energy to a much lower value, as shown here by blue. So, guys, we've gone from having an activation energy up here to decreasing it all the way down here. What that means, Year 11s, is that any decrease in activation energy will mean that more reactant molecules have got this energy available to them, in which case the reaction is going to occur at a faster rate. Now, guys, we can tie this decrease in activation energy into this graph on the left-hand side here. So, guys, if we take a look at this activation energy in purple, then we can pretend that this activation energy here and this one on this graph are the same value. Likewise, we can pretend that this activation energy here on this graph is the same as this one here. Because, guys, we're reading activation energy on this axis, so this represents a lower value. It represents a decrease in activation energy. What that means, year 11s, is that there's this number of molecules that have got that energy available to them. This number here at the lower activation energy is a much higher number than this number here at the higher activation energy. So, guys, essentially, the role, therefore, of the catalyst here is to decrease the activation energy and therefore increase the number of molecules with that energy available to them. If you increase the number of molecules with an energy higher than the activation energy, then you are going to be able to form products at a faster rate, and therefore there will be an increase in the overall rate of reaction. So, guys, that's a very brief introduction to catalysts. I'd now like to just touch for a couple of minutes on how we write a reaction if a catalyst has been involved. So, guys, I'll pick an example that we've looked at in class, and that is the decomposition of hydrogen peroxide. By decomposition, I mean breaking down, and that forms oxygen gas and water. So, guys, at normal room temperature with no catalyst present, this reaction proceeds very slowly, and in fact so slowly that you'd barely even recognize it was happening. It would take a very, very long time for you to decompose all of this hydrogen peroxide and form oxygen and water. So if we introduce a catalyst to this reaction in the form of manganese dioxide, then this reaction, guys, is going to proceed very, very quickly, and it's going to be very obvious that it's occurring because a whole heap of bubbles will be formed and you will be emitting a whole lot of oxygen gas. Now, guys, there's a reasonably important thing to note here, and that is that if a catalyst is present in a reaction, you should write that catalyst above the arrow like I have done here. What that tells the person reading this reaction, guys, is two things. Number one, that this is the catalyst present, and number two, it's above the arrow, which means that whilst it plays a part in the reaction, it is not consumed as such. So, guys, we will always end a reaction with the same amount of catalyst as we started. So whilst it has a role in the reaction, it doesn't actually get consumed in the reaction, and that's why it has to sit above the arrow like this to represent that it's not a reactant per se, even though it's actually present during the overall reaction. So, guys, that's a fairly brief introduction to the theory behind how catalysts increase reaction rate. In installment number 3, I'm going to discuss with you guys in a little bit more detail how we apply the use of catalysts to industry and everyday life in terms of catalytic converters in cars and the catalyst present in the formation of ammonia gas. So until next time, happy listening. Bye.